Hello and welcome back to Dynamic System Modeling. In today's session, we will be discussing the transform solutions of linear models. Namely, we will be discussing the Laplace transform, which is an efficient tool in the differential equations. So the Laplace transform of a function in the time domain f of t can be denoted by f of s. So simply the Laplace is a transformation or mapping from the time domain to a complex frequency domain S, which S is given by some real part plus the imaginary part. So f of s is the multiplication of the function f of t by each element n minus s of t. And then we would like to look over this multiplication from time 0 to time infinity dt. That's why we integrate. Now, if we are given a unit step function, and the unit step function, let's denote it by ut, and this is the time t. U of t is given by 1, it is equal to 1 for t greater than or equal to 0, and it is 0 otherwise, or for t less than 0. Now, if we are asked to find the Laplace transform of this unit step function, so the Laplace transform, let's denote it by f of s, the Laplace of u of t, it is equal to the integral from 0 to infinity of 1 multiplied by e power minus s of t dt. We took only the 1 because we are interested from 0 to infinity. So the integral of e power minus st, in general the integral of e power ut dt, it is 1 over u prime t e power ut plus some constant c. So the integral of e power minus st, it is 1 over the derivative of this part, which is 1 over the derivative of minus st, it is minus s, e power minus st, bounded between the time 0 and infinity. Now, we can examine the effect of infinity over the exponential function. Okay, so e power minus infinity, this is the exponential, minus e power 0. So as the time goes to infinity, okay, or minus infinity, then the exponential term goes to 0. Then, so e power minus infinity, it's 0, minus, this is equal to 1, e power 0, minus multiplied by minus is plus, and this is equal 1 over s. So the Laplace transform of the unit step function is 1 over s. And it is called unit because the amplitude of this is equal to 1. It can be a step function, general a, like this. So the step function, then simply you can obtain the Laplace transform of this step function u of t, and it must be equal to a over s. Now, if we are given the exponential function described in this figure, which is f of t is equal to e power minus at, if a is negative, then negative multiplied by negative, then this is a positive term, the exponential is increasing. If the exponent a is positive, then it turns out to be negative, and therefore we have a decreasing function. And now we are interested in obtaining the Laplace transform of this exponential function. So the Laplace of e power minus at, it is f of s, which is equal to integral from 0 to infinity e power minus at, e power minus st dt. This is f of t. It is equal minus s plus at dt. Again, the integral of this term of the exponential, it is 1 over the derivative of this term, which is minus s plus a e power minus s plus a bounded between 0 and infinity. Again, e power minus infinity. Okay, so this is s plus a e power minus infinity. Okay, this is time t. Sorry. So e power minus infinity, this is infinity, this is a constant, so this turns out to be infinity, minus infinity, minus the time is equal to 0, and therefore this turns out to be 0, minus 0. E power minus infinity again is 0 minus 1, which is 1 over s plus a. So the Laplace transform of e power minus at is 1 over s plus a. Let's take now the ramp function, okay? And the ramp function is defined by t. It is a linear function. F of t or rt is equal to t for t greater than 0, and it is 0 otherwise. So the Laplace transform of this ramp function is the Laplace of r of t, which is 0 to infinity t e power minus st dt. Now, in order to determine the integral of this two functions multiplied with each other, the derivative of t is 1, the derivative of 1 is 0, the integral of this term is minus 1 over s e power minus st. The integral of this term is 1 over s squared e power minus st. Okay, now we can multiply this term. This is positive, this is negative. So it is equal to minus t over s e power minus st minus 1 over s squared e power minus st. Okay, all bounded between 0 and infinity. Alright, now if we substitute the infinity, okay, at this component, then we have minus infinity multiplied by e power minus infinity, which turns out infinity multiplied by 0, which is indeterminate. So we have an exponential term, and we have a linear function t. We notice that the exponential term can reach infinity at the time t is very slow and it's still a number. So I can ignore this term or the linear function in front of the exponential function. So the limit as t tends to infinity of t power et, it is equal to, I can ignore t. Why? T is a constant, is some number, while e of t is reaching the infinity. This is still some constant number. Alright? So the limit of t tends to infinity is e power infinity, which is equal to infinity. The limit as t tends to minus infinity of t e power minus t. So again, I can ignore this term. E power minus infinity is 0, and this is equal to 0. You can deploy other methods like the L'Hopital rule and or any other method. Okay, to me, I prefer the method of looking which function is faster than the other. So the other will be a constant in front of the other faster function. Alright, so if we substitute infinity, this turns out to be 0. Substitute infinity, this turns out to be 0 again. E power minus infinity is 0. Now we want to substitute the 0 term. T, this would be 0, and e power 0, it would be 1 over s squared. So this is e power 0, turns out to be 1. Alright, so minus multiplied by minus is 1 over s squared. Great. So the Laplace transform of the ramp function is given by 1 over s squared. And if we perform the same operation over different functions, we can come up with this nice table which can summarize as the Laplace transformation of different function. This is the unit step function. And this is the ramp function, and so on. So in summary, we discussed the Laplace transform. However, we will be using this table in the upcoming sessions because our focus is not on the mathematical part. We are discussing dynamic system modeling, so we'll be using this table, okay, to obtain the Laplace transform of differential equations and other input functions. Thank you.